Hey folks, we're back with another video covering topics in the SOA's Statistics for Risk Modeling exam. Today's video covers Generalized Linear Models, or GLMs for short. There's a lot of new terminology and concepts, so we'll break down the formulas and explain everything in a way that's easy to understand. Let's get started. Here we plot fitted curves using three different types of regression models. Which of these could we call a generalized linear model? If you answered linear regression, you're correct. If you answered all of them, you're also correct. All of these are generalized linear models. The term linear in generalized linear models refers to the relationship between the coefficients and the x variables, not the relationship between the y variable and the x variables. Let's see how this works. Recall from multiple linear regression that the relationship between p predictor variables and the mean response variable y for observation I is given by the formula on the screen. GLMs take a very similar form. They also model the linear relationship between a set of predictor variables and the mean of the response variable. But instead of directly equating the expected value of yi, they can take the form of any of the formulas on the screen. Note that all of these are still linear in the coefficients. However, by expressing regression models this way, generalized linear models allow us to model a variety of different relationships between the mean of the response variable and predictor variables. We're no longer limited to a simple linear relationship. By the way, before we get started, you might find matrix notation in the source material on GLMs. I sort of get why it's used, but it's kind of confusing to visualize what the vectors represent without writing it out. Let's quickly discuss the two vectors used in the source material so you're familiar with the notation. X sub I represents the column vector of predictor variables. We transpose X sub I to get a row vector. The transpose is denoted by the prime symbol. Beta represents the column vector of coefficients. The dot product of these two vectors gives us the familiar form of a linear regression model. Now whenever you see a vector, you'll know that it's just shorthand to represent several variables or coefficients at once. Let's provide some definitions around GLMs. Define the systematic component, eta sub I, as the linear combination of x sub I and beta. Next, we define the mean response for all observations I as mu sub I, which is the expected value of the response variable y sub I. The function g is known as the link function, where g of mu sub I is equal to the systematic component. The link function is called the link function because it connects the systematic component to the mean response. Let's look at an example to understand this better. We'll start with the familiar simple linear regression model. In the familiar relationship, yi equals beta 0 plus beta 1 times xi plus epsilon I. If we take the expected value of both sides, we get e of yi equals beta 0 plus beta 1 times xi. Notice that the left side of the equation is the mean response, and the right side is the systematic component. Recall that the link function g establishes a relationship between the mean of the response variable to linear predictors. With some algebra, we notice that mu sub I equals g of mu sub I. So the identity function is a link function for simple linear regression. It turns out that this identity function is also the canonical link function for the normal distribution, which we'll discuss in more detail later. Let's look at another example where the dependent variables are binary. Assume we want to model the probability of passing exam SRM given X number of hours studied, where each observation y sub I can take a binary response of 1 for pass and 0 for fail. We can use logistic regression to model this behavior. By taking the log odds of the expected response variable, we constrain the response variable to range from 0 to 1, reflecting the probability of passing the exam. Notice that the left side of the equation is the logit of the mean response, and the right side is the systematic component. After bringing in the link function, we notice that the logit function is a link function for logistic regression. Similar to how the identity function is the canonical link function for a normal distribution, the logit function is the canonical link function for the binomial distribution. We'll cover how the canonical link function is derived later in the video. In this section, we're going to bring in some outside knowledge. As it relates to the exam, this material might not be tested directly, but I think it's helpful in understanding why GLMs are used. To recap, the link function establishes a relationship between the mean of the response variable to linear predictors. It does not transform the response variable. There are several benefits to using GLMs. First, GLMs accommodate various probability distributions, making them suitable for a wider range of data types such as count data or probabilities. They also provide more flexibility, allowing you to make explicit assumptions about the data's distribution and its relationship with the predictors. For example, if you wanted to, you could say, "My data looks like a Poisson distribution, and the relationship is logarithmic," and use a GLM to model that behavior. Finally, GLMs avoid the potential bias and interpretation errors that transforming variables can introduce. Let's look at an example to see what I mean. Suppose you observe data that follows an exponential distribution. So, you transform the data by taking the log of the response variable. You then perform ordinary least squares on this transformed data to fit a linear model. And finally, you transform the model back by taking the exponential. This introduces bias in the estimation of y. However, with GLMs, we do not transform the response variable. Instead, we use a link function to transform the mean of the response variable. This allows us to always get back to the true mean using the inverse link function. This inverse function is known as the mean function. One of the requirements of a link function is that it must be invertible so that we can always calculate the mean response from the linear predictor. The linear exponential family of distributions is a class of probability distribution functions that can be expressed in a specific form. It models the behavior of the response variable y. The probability distribution function takes the form f of y given theta and phi equals the exponential of the quantity y times theta minus b of theta, all divided by phi, plus s of y and phi. In this formula, y is the dependent variable, theta is the parameter of interest, phi is the scale parameter, b of theta is a normalization function, and s is a function that depends on y and phi but not on theta. The PDF of common distributions, like the normal distribution, can be written in this form, which we'll demonstrate later in this video. For distributions in the exponential family, the mean and variance of y can be derived from the function b of theta. We can calculate the mean of this distribution using the expected value calculation from exam P to get e of y equals the first derivative of b with respect to theta. And using the variance formula from exam P, we get that the variance of y equals phi times the second derivative of b with respect to theta. A quick note about the variance. Recall that in linear regression, the variance of the response variable is constant for all observations. This means the spread of the data remains the same, regardless of the magnitude of the prediction. This assumption is necessary to estimate the minimum variance unbiased estimator when running least squares regression. For GLMs, we relax the constant variance assumption. In these models, the variance can change as a function of the mean. This changing variance plays a critical role in estimation and inference in GLMs. The variance function, v of mu, depends on the distribution of the response variable. For a normal distribution, we have constant variance. But notice for Poisson, the variance grows as the mean grows, and for gamma, it grows with the square of the mean. The choice of the variance function, rather than the distribution of the response variable, drives inference properties. Earlier, we mentioned link functions. A particular distribution may have several suitable link functions. The canonical link function is a specific link function in the exponential family, where g of mu equals theta. This relationship ensures that the systematic component is equal to the parameter of interest theta, which simplifies the mathematical formulation and estimation of the model. Let's go over the canonical link functions for common distributions in the exponential family. If the response variable follows a normal distribution, and we let mean function equal theta, then the canonical link is the identity, g of mu equals mu. For Bernoulli, if the mean function is e to the theta over quantity 1 plus e to the theta, then the canonical link is the Logit function. For Poisson, if the mean function is e to the theta, then the canonical link is the natural log. The gamma and inverse Gaussian distributions also have their own mean functions and canonical links. The canonical link function is intuitively appealing and often leads to simpler computations and more straightforward interpretations. Let's see if the normal distribution is a member of the exponential family. We start with the normal probability density function as a function of the mean, mu, and variance, sigma squared. We want to see if we can rewrite this in the exponential family form. Define the components as theta equals mu, phi equals sigma squared, b of theta equals theta squared over 2, and s captures the remaining terms that depend on y and phi. Let's plug in these components into the exponential family form to verify that the normal distribution fits this form. First, we substitute theta with mu. Next, we substitute phi with sigma squared, the variance of the distribution. Now we substitute b of mu with b of theta, which we identify as theta squared divided by 2. Finally, we substitute s of y and sigma squared, which includes the remaining terms from the normal PDF. Simplifying and combining terms, we see that this expanded form is equivalent to the normal PDF we started with. Since the normal distribution can be rewritten in the exponential family form, it is a member of the exponential family. Just as a reminder, exam SRM mainly tests conceptual understanding and basic applied math calculations. This level of algebra is already beyond anything you'll need to know for the actual exam. Recall that the canonical link function is the link function that equates the mean function to the canonical parameter theta. Since we defined theta to equal mu earlier, the canonical link function is simply the identity function, where g of mu equals mu. To recap, in this video we covered why GLMs are called linear models, specifically that they're linear in the coefficients, not linear between the response and predictor variables. Key definitions, including the systematic component, link function, and mean response. Why GLMs are used over transforming the response variable, and how it offers flexibility in modeling. The linear exponential family, the variance function, and the canonical link function. Unfortunately, the source material on GLMs is dense with formulas and doesn't always provide the intuitive understanding you need. Because of this, a big portion of the information in this video was compiled from several external sources. Although GLMs is one of the more difficult topics on exam SRM, I wouldn't necessarily spend too much time on this section if you're strapped for time. Because the source material is formula dense and exam SRM is a more qualitative exam, there are plenty of other topics that are more likely to be tested. But if you're not in a time crunch, then GLMs are definitely worth a review. If you liked this video, be sure to hit the like button and subscribe for more content. Thanks for watching. For a comprehensive written course, hundreds of practice problems, progress tracking, and AI-assisted tools, visit the Actuarial Nexus. See you in the next lesson.